So, right. So, by the way, hi everyone. Good evening to all of you. I'm Suraj. I'm the co-founder and CEO at Decibels Lab. I'm also the course director. I guide the team in creating curriculums and syllabus at Decibels Lab. Also, we support a lot of project activities to support some of the two-wheeler manufacturers and also three-wheeler manufacturers. So today's topic is to discuss about EV powertrain simulation, right? So how does the powertrain, if you want to decide anything for EV, so how do you actually like decide upon what size of the motor you want, what size of the battery you want? It can be so simple that we just can go to a market and buy some motor, but it is not really like that in a professional world. Every single watt of energy makes a lot of difference. If you drive about 1 lakh kilometers, it's about 1 lakh watt of energy, right? That's a huge amount of wastage if you do not do it properly. It's not just about at the vehicle level, as I always say. Even the recharging of the battery also takes a lot of losses, and production will take a lot of losses. So it makes a lot of meaningful sense to actually use proper simulation tools to perform simulations that you can arrive at the right component sizing and powertrain packaging and stuff like that. So with that as a motivation talk, we will just start ahead with the content. So any one of you who is here, I would like the session to be interactive. As much as it is interactive, you will be also able to learn a lot out of the session. Okay. I have already mentioned some lines here that why do we actually perform simulation. Any one of you know why do we actually perform simulations? What is the objective of you performing any of the simulations on the powertrain? Anyone can answer it. So it will be really exciting and interesting to interact. So you can also unmute and speak, and let us know, why do you think you have to perform a powertrain simulation? What is
in
the fun?
order to in order to know the distribution of the power within the system so that we can analyze the concept.
All right. So you want to analyze the distribution of energy across the system. Great. Fantastic. Okay. Repeatability. All right. And to reduce prototyping cost. Okay.
To find the performance of the system.
Performance of the system. Fantastic. That's really correct.
To avoid failures.
I'm sorry?
To avoid failures.
To avoid failures. Okay. Okay. Perfect. And see the performance before finally manufacturing in real world, to know the behavior of a system before actual implementation. Great. I think most of you guys are pretty much there to answer the questions. Thank you for participating in to imitate the real process. Fantastic. So to a very simplistic world, right? So building an EV seems very simple, but when the company like Tesla, why do they have to put so much of perfection into everything, right? They can also build another normal EV, but there's a lot of difference between just building an EV but building the best EV. All right. So building a best EV is about taking out, it's like a creating a vehicle which can give you like 40 kilometers of mileage, right? Take a car, let's take an example, right? It is wonder of worth, right? So and what Tesla is doing today, maybe like even at their system level, they're trying to optimize everything to the most best of it. If you talk about battery pack, they have the best energy density. If you take a cell level, they have best energy density comparisons, safety level comparisons. And if you take about energy consumption for their segment, they are doing really amazing work. If you consider about energy consumption by your HVAC system, like an auxiliary system, they have done the fantastic innovations in terms of it. Or also, if you take examples of component sizing, architecture development, weight targets, drivetrain targets, all of them are to the best and best. The efficiency of all the systems to work at a synchronization. So when you do everything to the best of it, then your system performs really best. The end results is basically the vehicle is not only performing, but the vehicle is very energy efficient. All right. So that is one of the idea why you could just get a very bigger picture on, we have to start simulations. But on the other side, which I define here is, the powertrain is a non-linear system. Okay, it is impacted by various different factors. So as an engineer, we try to fix them within the constraints of the function. So what do I say here is, let's say the very basic fundamental thing is that you want to meet the performance. Let's take a very simple example, right? So if you want to go from 0 to 60 kilometers per hour, let's say in 2 seconds, okay, that is what your vehicle target is. Let's say a customer from some company will give you the project like that. So how do you try to achieve that, right? So first of all, a very simplistic, okay, you can put some acceleration, F is equal to m into a, and then a rolling resistance, aerodynamic resistance, gradability, zero grade because it's acceleration test. Let's run your simulation. You get your results of your wheel torque, then you arrive at your motor torque, and then you arrive at your battery currents. Like, okay, this is fantastic, right? It's a very, very simplistic process. But the same vehicle will not be able to perform at 10% lower SOC. Let's say at 100% SOC, it can behave better. At 50% SOC, you can't expect the same acceleration, right? At 10% SOC, it is impossible that you can achieve that acceleration, right? It's a very intricate part. So, but can you actually build a bike and then test it? No, you really cannot do it, right? It's very, very expensive. And for that, then you have to build a simulation models so that you can study and how does your actually vehicle perform at different conditions. So I give you an example of an acceleration test, right? Now with that acceleration test, as I said, if you have a battery SOC 100%, then your vehicle can achieve acceleration test within 0 to 60 in 2 seconds. But what if it is not? Let's say it is at 50% SOC. How do you represent that your vehicle will not be able to perform same, right? So now for that, you need your battery model, correct? A simulation model of your battery, so that it understands that, okay, I have a limitation of state of power that I can give you as an output because my battery SOC is only 50%. If it is 40%, you need to have a model that basically represents the realistic scenario of the cell or a battery pack in the real world, right? So like this, if I start talking about a lot of complexities, let's say thermal behavior, right? If the battery temperature is at an X point, then you can't actually extract as much as energy that you can extract at an optimal temperature of the battery. So like this, a lot of considerations will come into a picture that if you want to develop a powertrain, okay, it's not just basic equations of physics, and then you can just derive some torque and basic values, and anybody can do it through the Excel. But when you really start to develop something to the core of it, and then you want to know whether the system really performs like this, and then you want to build a powertrain level model that talks like, okay, if the battery SOC is this much, only my performance is this much, I need to implement it, and derating algorithms and all this stuff. So that is when you need a complex model, right? You can't do it with your hand calculations. You can't just do it with your Excel sheets, right? It is much more complicated because you get thrown out with 60 to 70 graphs, and you can't analyze all of them without having a proper simulation tools. And that is why you require a simulation tool, because when you say it's a non-linear system, the behavior is very erratic, right? So when it's a linear system, then you can put some equations and try to derive it. But here you need to study all the scenarios. That's why you need a simulation first of all, so that you can be able to perform modeling and then build the simulation studies in place. Now let's kind of go through all these things, and then we'll take a deep dive into each of subsystems. I think at a larger level, everybody know what is there in EV. This sessions has been going on from quite some time, and now we will try to understand a little bit of a design approach. So at a very simplistic level, as I said, the overall idea comes like this, right? You have all your influencing factors. That is your potential energy. That is then aerodynamic forces there, kinetic energy is there, and rolling resistance is there, and things like that. And then you have your tractive power. Basically, if you sum all of these things, then you arrive at your tractive power requirements, right? So if you say you have a transmission, you can just put the transmission basic gear ratio calculations. Then you can put also the efficiency of transmission. Then upon that, okay, it is a type of motor. If it is an induction motor, at some basic level of calculation, you can just put 2.8 by 60 as well to perform simulations. But yeah, if you want to develop a very decent model, then you can go and model the little advanced of a motor model as well. You can define a lot of motor constants and motor parameters and stuff like that. So you can predict really the maybe its losses, its efficiency, its current, its voltage, and all the parameters. And then also a little bit of a inverter model where it talks about controls and stuff like that. Then on top of it, then comes a little bit on the traffic losses or auxiliary powers. So what is auxiliary accessory powers? It's like, let's say when we go back to the slide, you have a lot of other systems. Basically, the battery energy is used not only for the motor and a transmission, right? The battery energy is also, the battery energy is not just used to drive the motor. For example, the battery energy is also used to cool the motor if it is hot. It is used to cool the inverter also if the inverter goes above a specific limit, right? Or maybe it's an onboard charger as well. And then the battery pack energy is also used to heat the cabin or to cool the cabin as well, right? It is also used to charge the auxiliary battery like a 12-volt battery or all the other 12-volt system. Basically, that the primary battery is the component that gives the energy to all the components, right? Until now, we just think about tractive systems, right? But apart from tractive system, there is something called as the auxiliary system also. So they also consume some amount of energy. So we need to model all of them. And then any of the other basic auxiliary system also you can put. At the end goal is we will think about SOC, right? And obviously some other parameters in place. So this is a workflow process typically any. So 1 second, yeah. So sorry, I think I have some internet issues. So if you guys are not able to hear me or any audio issues out there, you can always let me know so that I will possibly try to manage a session in a better way.
Sir, can you, hello?
Yeah, please.
Can you repeat what's an auxiliary battery or auxiliary system?
Okay, so auxiliary battery or auxiliary system is this, that let's say, yeah. So we have the air compressor, okay? And what is this AC compressor? Not air compressor, apologies. So air conditioning system. Basically, when the engine was there was a belt that connects the compressor and compressor is to run. And then that takes care of compressing the, that HVAC system cycle, right? Now the compressor cannot be connected to a motor, right? So that is motor is sitting somewhere else. And it is having its own complexities in terms of load requirements. So now you need to actually have a motor that runs the compressor, right? If it is a motor, then you have to supply the power to that motor. So that's how the compressor will run. So then if you turn on the AC, that means you are consuming some amount of energy from the main battery to the compressor and to run the whole system of air conditioning system so that it will run and provide you a cooling effect. That is basically called as a parasitic loss. Not say like it is called as a parasitic loss in engines if it is a engine oil circulation and stuff like that. Now here you can call it as an auxiliary loads. Or if you want to cool the motor, so you need to supply the coolant, right? Or like it's typically a coolant. And then in that cases as well, you have to actually cool the like first have a refrigerant, and you can bring that refrigeration cycle. You can have a heat exchanger system between the refrigerant and the coolant, and then the coolant will flow. For that, you need to have a pump to run the coolant in place. So this is all the system that happens through. When I say there is any system that is except supplying the energy to the motor and to the wheels, it is called as an auxiliary loads. What is an auxiliary battery? So in most of the cars today, we see this 12-volt battery. That means this battery will be somewhere about, let's say, 250 volt, right? So this battery is majorly used for driving the vehicle, but this battery is used for powering up all your 12-volt system, like maybe ECUs or VCUs or basic HMI systems and stuff like that. Not only it always drives, but there can be another system as well which can directly convert 250 volts to 12 volts as well. But auxiliary battery is there, let's say when a vehicle is shut down, you need to have some amount of input to turn on your keys and stuff like that. Because when you put a key on, it will not directly trigger the high voltage system. First, you need to power up a low voltage system, and then you need to go to power up a high voltage system. So in that way, you also need a battery that is called as an auxiliary battery. So I hope I answered your question.
Yes. Yes.
Okay, great. So thank you for asking the question. If you have anything, you can always ask. All right. So first and the foremost starting phase is something called as a drive cycle. Okay. So a lot of people like think that we can actually develop the powertrain simulation with some IDC cycle or MIDC drive cycle or a WLTP drive cycle or a NIDC drive cycle or something like that. So whenever we think that we can develop something in a simulation, right? Simulation is basically garbage in, garbage out. It is like whatever the value you give, it takes some synthesis and then you give you an output. If you give an incorrect value, you'll get incorrect results, right? The same way, it is very, very important that the drive cycle that you feed into the simulation model has to be completely perfect. It means if you're developing a bike and in that you're developing a scooter, okay, or in that you're developing a scooter for a basic one or a something like Aether, you have to be very, very specific about how you drive the vehicle. It means how the driver, actually how the customer will use your vehicle, okay? Or if you take a three-wheeler, if you take a four-wheeler, if you take a car or a bus, it means the government has done some standards, IDC drive cycles or MIDC drive cycles or something like that. But those are unrealistic drive cycles, okay? That's why you get a ARIA testing range that, your bike will give you like, 200 kilometers range in a single charge, but in the reality, it doesn't give you, 140 kilometers as well, all right? So if you use the similar drive cycles, it becomes useless to perform simulations. So you have to have proper drive cycles so that you will be able to, get the correct results. That would be the very, very first important fundamental step of simulation. And this data talks about operating points, okay, where it is deriving from the drive cycle. If you take a different segments, right? So if you take an example like a sports car, right? So your expectation is to go to a very high speed and then in a very less amount of time. But if you take a city car, right, you want some decent medium speed, about let's say 120 or something like that, but you don't want that to be achieved in, let's say, like 5 seconds. You're okay if you accelerate to a decent value as well slowly. So basically, these are the characteristic graphs that will give you as an input data to your simulation model. That means that you need to know what vehicle segment you are in, and then you need to create a realistic drive cycles. So great. In the same way, let's continue ahead into the next slides. So there are a lot of different drive cycles. Okay. Basically, these are the drive cycles that are currently available. Okay. But if you take these drive cycles, if you consider this drive cycle, and this one, they each of them have a very specific characteristics. The first one is WMTC. That's part one of the drive cycle, or it's a JP10 15 drive cycle, and then you have UDDS, and then you have Manhattan drive cycle. If you see, this is basically a city drive cycle. Okay, if you take a bus example, right? See, the bus is like, okay, it starts, it goes and achieves some speed, and then again it comes back, and there's somebody in front of you, or there's for example, this is for 200 seconds, right? So within the span of, let's say, about 10 minutes, let's say 600 seconds, right? 10 minutes. If you see the number of times the vehicle has stopped, right? It means when the vehicle is stopped, it has to come back. It means it needs a lot of torque. The way it behaves, its characteristics will be slightly different. Okay. But if you take a vehicle like, the highway, like, urban drive cycle kind of a scenario. So, and typically this scenario is like a urban drive cycle and scenario. So where you see there's a lot of timeline between each stop, right? Like there's a one and then 1 year. And then the scenario is here. There is a timeline between the stops, but here there are frequent stops. So in these scenarios, the data that comes out of your simulation model will be quite important to make your decision. So it means that you can't just use some generalized drive cycles that are available globally to make your decision. You need to use proper drive cycles so that you can make a decision. So we have done some comparison studies of the data of a drive cycle. So each of them exhibits a specific characteristics as I was talking about. Leave about the distance, it is not a parameter. But if you see a top speed, like this WMTPC talks about 59, the JP 1015 talks about 70.9, or UDDS talks about like as I said, a highway drive cycle, a semi-highway drive cycle, and a city drive cycle. So the values are completely different, and all of this will give you a lot of insights in simulation, in performing your simulation studies of the results. So in this way, we have developed, there are multiple types of drive cycle. This is just a reference. Okay, that means when you're a simulation engineer, you need to first and foremost important thing is get your proper drive cycle to perform any simulations. So in this scenario here, there is something called as an urban, there's a rural, then there's a highway, and then there's a maybe you can call it as an acceleration drive cycle, gradability drive cycle, and obviously this racetrack is not really required because you're not developing a vehicle always for a racetrack. So the close observation, if you see, the average speed will be different for each scenario. Maybe highway means obviously you're driving at a higher speed. If you compare an IC engine with an electric vehicle, the electric vehicle will give you lesser range in highway, but more range in the city. But if you take a petrol vehicle, it will give you more range in the highway, but less range in the city conditions. So like you really have to actually test the vehicle and get the results on this. But how does your simulation also correlate with this? It's a fantastic understanding all in together. So if you compare this and this, what do I say? Or let's say this and this drive cycle. So that you see, like there is no stop here. Because in racetrack, we don't stop, right? Only the time you want to stop is either you get an accident or possibly at a end of your race. So you don't want to stop anywhere in between. That's why you don't see any stops. Like there is no zero speed in place. And there is sudden accelerations always. Like you want to achieve the quickest amount of acceleration in a very shortest amount of time. So input is very important to get a proper output. There is one question. What if we use a region braking in highways? See, it is possible, definitely, but you need to possibly study what kind of speeds you're at if you brake, what kind of region current you may generate, and whether that region current can be taken by battery. A lot of scenarios whether the battery temperature is in the good condition to take a region. A lot of these scenarios will come and you will be able to define it. Okay, so all right. So this is one part of it. And the other side as well, if you continue to discuss about a drive cycle, this part of the drive cycle talks about driver behavior, okay? Our performance of aggressiveness. What I want to tell you is when you develop a bike, you may have to consider kind of customers they may be. If you sell the vehicle to a very young driver, he may just accelerate a lot because that's the typical nature, it is an aggressive driver. If you give to somebody who is about like 35, 40 age, they may drive mild because they have seen through a lot in life. And then if you give to somebody like 70, 65, 60 age or something like that, they may drive it very calmly and easily. So the vehicle, if you drive it very aggressively, it means you're demanding a lot of current, right? If you're demanding a lot of current, obviously it will impact the battery performance, and then it will also impact the range as well. So, but it is good always that, okay, what is your driver behavior is, and then just put the driver behavior, how your vehicle is going to perform to give you output results in place. So any questions from anyone? So in the next part is, until now I talked about all the type of drive cycles. This is something like a real-time drive cycle. Okay, so it means the way you realistically drive on the road. It is not like very plain drive cycles like what you see here, right? Not a very simplified drive cycles of this kind. But when you really drive the vehicle, the scenario looks like this. And we have developed some of these cases to collect some data. So about 4,500 seconds of data has been collected when somebody drives in a specific road patterns and stuff like that. This looks to be like more like a part of the vehicle is driven on the like a medium or very low traffic condition, and then maybe join into the highway or something like that, or possibly something like a basic racetrack scenarios in place. So here is a comparison of a different driver levels: aggressive driver, normal driver, and economic driver. The only scenario you see is the aggressive driver pushes the vehicle to the maximum. Imagine somebody is a race driver. Okay, they are very well experienced. Okay, they can abuse the vehicle as much as possible because they know how to torture the vehicle to the best of it, or extract the best out of the vehicle, because they know to handle the vehicle in a better way. So when a person drives, you can expect, okay, the vehicle can perform, but it won't be able to give you a range in a specific parameters. Some of the scenarios also comes into a picture, so that you will be able to analyze them to the information. The idea here is, if you give a right input, you will get a right output from the simulation. Power drawn from the battery pack with respect to speed, it is typically, see, both. It's another day a torque that really demands the current a lot from the battery, because the torque is directly proportional to current, and current there is directly proportional to flux. All right. So in that way, it is typically the torque that demands the current. On what parameters a drive cycle is drawn? See, it is not drawn, it is created in the real-time testing. You need to take a bike, you need to have some sensors, then you take the vehicle on the road, and then you collect the data, you come back, you filter a lot of the data that you have, a lot of signals will be there, a lot of errors will be there, you then generate a drive cycle. Cool. So then the next point is basically on the operating points. So what exactly the operating points is meaning by? As you already may be knowing that the motor operates best in some points. Okay. If you see, the efficiency here is 98%. Okay. If you see, it is 84%. It's about 93 here. So if you try to operate your motor within some limits like this, right? Some of these limits, that means that the motor is operating at a higher efficiency. What is the meaning of higher efficiency? It means the motor is going to consume less energy, but give you a better output. So if you consume less energy, then it is going to be less energy at a battery as well. If it is less energy at a battery, you will expect a better range. So imagine you have developed a vehicle and it is operating at inefficient regions. Maybe like it is operating towards too much here in this region, or like a lower efficiency points, something like maybe in this region or something. That means it is very highly inefficient. If you try to operate your motor at an inefficient region, then you will get an inefficient range. And then why? Because there are a lot of losses, and those losses basically convert to a heat, and then again that heat will impact the motor performance itself. So it's a very bad condition for the motor. So try to always design the motor, or choose a motor, or choose a transmission, and to meet your performance in the right way, that it is optimally designed. You can observe some of the graph like this, that whenever somebody drives, the SOC drop, so that if, depending upon the driver performance and stuff like that, you can see a various different prices, SOCs. If the driver is aggressive, you can expect, because the area under this curve represents the charge, right? You can expect as the range that it represents the charge, and then you can convert it to a range as well. So then some of the scenarios that I'm trying to present for the simulation case studies is the temperature of the motor is also important, because the efficiency of the motor also depends upon the temperature. It depends upon the first torque of the motor and RPM of the motor. That is a basic consideration. Apart from torque and RPM, it also depends upon the temperature. If the temperature of the motor is too high, then the efficiency of the motor will also be very bad. Actually, this is not the efficiency map, temperature map, but the temperature map will also look something similar. That you see the red region is highly efficient, and then it goes bad here. The same way it is with respect to torque and speed. You can also expect temperature here in this column. You can see that efficiency has been lesser at a higher temperatures as well. And considering the battery modeling side, when you have a battery model, the battery behaves differently at different temperature conditions. If you draw 3 amps at 20 degrees Celsius, the cell exhibits some characteristics. If you see, the cell is more comfortable at 40 degrees Celsius, right, in this condition. It means the area under this curve tells the capacity. If the same cell, if you draw if you draw 3 amps at minus 20 degrees Celsius, the capacity that you get is only this much. Okay. So it means there are some parameters you need to also put in your model, that if the battery temperature is going above specific limits, the amount of capacity that you can expect is only this much. And if that temperature variations are too much, you should be able to develop a active cooling system that to ensure you will be having a battery within the specific temperature limits in place. So then there's an auxiliary system. I was calling it as a HVAC system. They also have an impact. Okay. So what exactly it is meaning is, as the ambient temperature goes higher and higher, okay, so the estimate single the range of the vehicle. So what I meant to tell you with this graph is, if the temperature of the atmosphere is higher, it means you require more energy to actually cool the cabin, right? If you require more energy to cool the cabin, that means you're trying to draw the energy from the battery pack. So either in the other side, if you have to heat the battery, if the temperature is, let's say, like minus 10, minus 20, you need to heat the vehicle, or on the other side, you need to cool the vehicle by turning on the AC. So both the ways you will consume energy. If the temperature is higher, obviously energy consumption will be also higher. So yeah, that's in a very, very, very brief overall way. I would like to bring some conclusions by end of the session here. Does anybody have any queries or any questions that you would have? And I'll just give you a 5 minutes of brief through on approaches of simulations in a simple way. Anyone have any questions?
Sir, what was SOC in the previous slides?
Okay, the SOC is called state of charge. It means the amount of remaining capacity in the battery. Let's say in your mobile phone, you will see like 60% is there. 60% is basically the amount of capacity that is there inside the cell.
Sir, can you show me some tabular columns? Before the temperature slide, there was some tabular columns factors. Yeah, what is, yes, this correct. What is exactly, so can you explain this?
Sure. So basically what we're trying to understand is like different drive cycles, okay? And what is the typical energy consumption scenarios in place, okay? So I think the overall idea here is it is related to a specific drive cycle. That should be the scenario. The real-time drive cycle, what I meant to tell you, I think here is the expected energy consumption. How does it reduce with respect to your drive cycles? Let's say this is drive cycle A, this is drive cycle B, this is drive cycle C. Okay, but the same vehicle. The vehicle is same. Maybe even in cases the driver can be same, but he drives a little bit aggressively here. He drives very slightly mild and then very calm or easy here. So what exactly it tells is like the energy consumption with respect to the specific drive cycle scenarios. If the driver is too aggressive, energy consumption is also higher. And obviously the watt hour as a total energy consumption also be higher. But it can be the same but energy consumption can be different in different scenarios. This is the comparison study which we typically make. Let's say we take any vehicle, we perform the city, highway, semi-highway, or a urban or a highway combined together. We create multiple drive cycles and then we compare the energy consumption studies basically. Okay. Any other questions?
Hello, am I audible?
Yes, you're audible.
Okay, so what I conclude from your presentation is like, suppose we are modeling a powertrain. I mean, like a simulation where powertrain modeling simulation is done, then we have to check with the different drive cycles which are available, right? To analyze the performance of that powertrain, right?
Yes, that is. I meant to tell you is the drive cycle will be very important to do a component sizing.
Right. Okay. Fine. So one more thing, like if you want to do that simulation, whatever data that you have represented in graphs, all these data be the specification data that you might have got from the individual components that we use. Maybe like
Correct.
that, likewise, right?
Correct.
So taking all those aspects into mind, we have to check the performance for different drive cycles to get how the powertrain will be performing, right?
Correct.
Yeah. Okay. Thank you.
So because if you sometime what happens is you have data, but sometimes you may not have all the data. So you have to assume some data and then arrive your model to a more more better accuracies as we mature the data as well.
Right. Actually, in this automobile industry, can you refer some of the softwares that they basically use for powertrain design,
See,
other than
largely,
I'm saying?
Sure. So largely people use MATLAB and GT Suite is also there. Altair is there. And people are also using AVL. They have few softwares for powertrain simulations. Yeah, this is the largely used. Each of them have its own capabilities. They have integrated simulations as well. Like if you take Altair, they have 3D, also 1D. MATLAB has 1D extensively. They have 1D simulation tools. So, but they can integrate 1D and 3D. 3D means you can do a CFD, right? It is 3D. So you can
I'm
turn
sorry.
the
What does this D means?
like it's a like one dimensional means you would study with the only equations.
Okay, fine. So if it is 2D or 3D means?
2D we don't typically have today. So 3D is there. 3D means where you have like a realistic battery pack itself.
Okay, are you relating it to the lab car models?
Lab car, yeah. See, I have not used lab car to give an exact answer. So what I'm going to tell you is, let's say if you want to estimate a temperature of battery, okay, how do you do it in your 1D simulation? You will say consider the resistance of the battery, resistance of bus bar, resistance of all the other materials, and conditions of the whole battery pack environment. So this is what you do. You write equations for each of this and run the simulation. You will get the temperature. But in
Correct.
the 3D simulation, it is not like that. You'll actually design a 3D model and then you perform a thermal simulations for that model.
Okay.
Hello, sir.
Hello?
What was the tool you have told sir, for 3D simulation?
I'm sorry. Which one?
For
Sir,
3D
is it audible?
simulation.
Sorry, let's go one by one. Yeah, please.
For 3D simulation, for 1D simulation, you referred MATLAB. For 3D simulation, what tool you referred?
See, Altair is there. They have
How you spell it?
Altair. Altair.
ALTIR. Okay.
Altair. Altair.
Okay.
So even GT Suite is also there.
Mm.
You can use. There are multiple toolboxes are there.
Suppose I want to design the powertrain as a prototype. So from basically from where we have to start. So how
Okay,
you will give you guidelines for this in
surely.
such cases? Yeah.
Okay, okay. So let me just. I was supposed to come to that point to deliver the session here. I will just do that in another 5 minutes. Any other questions is there? I'll take it and I'll tell you how it is.
Sir, I have one question.
Please.
Sir, actually, in recent years only we have a development of electric vehicles.
Mhm.
Okay. Before the emerging of electric vehicles, there should be definitely a benchmarking data will be there, right?
Correct, correct.
Yeah. So which vehicle was taken as a benchmark component, and what are the parameters they will consider benchmark data before designing an powertrain for EV?
Right. So typically, the benchmarks, you see, the thing is, it depends upon segment to segment. Let's say there is a KTM Duke 200, KTM Duke 390 as well.
Yeah.
So it is a vehicle segment that you always have. See, what are the specifications of your vehicle segment? Like acceleration, 0 to 60 in 10 seconds,
Yeah.
right? So, or top speed of the vehicle, right? And
Yeah.
then your mid-range torque, what do you want as a, let's say you are going at 100 kilometers per hour and you want to overtake somebody on the highway. How does the motor should perform? What should be available torque at some specific mid-range operations or top end operations and stuff like that? So at a very basic level, you take this as a performance requirements, right? To start with. And
Okay.
then
Okay, sir.
you will start to define your energy consumption. That means, okay, I want a vehicle to only, I want a vehicle to give about 100 kilometers range, but I want to use only like 2 kilowatt battery pack or 2.5 kilowatt battery pack.
Okay.
Right? So how do I put my system into a place? What is the weight of the vehicle that will come into a picture? Radius of the tire will come into a picture. Then your chain sprocket to sprocket ratios will come into a picture.
Yeah. Yeah.
Then obviously frontal area, rolling resistance, all these parameters. But typically your vehicle performance is your fundamental requirement.
Okay. Okay. Fine.
Yes.
Sir,
Yes, please. Hi.
sir, can you open please 19th slide, sir?
Yes.
Sir, here the torque is inversely proportional to speed. Is it correct, or sir?
Which is here, right?
Yes, sir.
It is correct.
Sir, then what happens? The torque is directly proportional to speed, sir.
What happens if torque is directly see, I mean, you will have the limitations of the motor to perform, and there will be some kind of not a straightforward relationship. You can't develop a motor which will have a exact curve as the RPM to a torque relationship. There will be electrical design considerations itself will be like that. So, or else like your packaging considerations will be also like specific to the way the motor has to be put into some vehicle or a specification. So there has to be some relative values, but I didn't clearly understand that how you wanted it to be relatable.
Sir, in the chat box, somebody written that it is basically depends upon its own resistance.
Own resistance?
Torque. Basically, the torque is a type of resistance. Has put a message in the chat box, sir.
Okay. So see that the torque, it's not a resistance. I mean, it is the output that motor provides to.
The motor provides output is the speed, sir.
See it. Okay. Maybe you have to really look into the basic idea of when you were in school days. I don't know whether you have done it. You used to put a cycle on the center stand and try to run the wheel. Okay.
Yes,
So
yes,
when when you try to run the wheel, you used to put a lot of efforts.
yes,
So
sir.
once the wheel sort of run, it has a momentum and it runs faster, right?
Yes, sir. Yes, sir.
So the thing is, imagine, can you connect a very low power motor, the motor that can run 1000 RPM, but
No,
if it
sir.
will not have enough torque, it will not
Yes,
be
sir.
able to move the wheel.
Yes, sir.
So it means you need the vehicle motor should have the torque, also should have a power. Okay.
Yes. Yes,
So
sir.
it is not like the motor just can run. It should be able to. It can run 10,000 RPM as well. Let's say you have a motor that is used for dental applications.
Yes, sir.
You can't use that motor to run the bike. It can run 20,000 RPM as well. You have a drone motor, right?
Yes, sir.
So that runs about 15,000 RPM. But not every motor is applicable for every application, every other application. So there is a characteristic that is required to meet.
Okay, sir.
Okay. So
Sir, here what is meant by leaf motor, sir? LEAF.
the Leaf is basically Nissan Leaf. Nissan Leaf is a product in the vehicle market. So basically, this motor graph is from the Nissan Leaf.
Okay.
Hello,
Yes.
is it audible?
Yeah, it is audible.
Sir, I think this motor torque characteristic is somewhere constant power and constant torque mode.
See, I mean, a lot of characteristics details are there. I think what exactly you wanted to ask?
I'm asking that if constant mode is there, then speed is increased, torque is decreased. Like the curve is.
Right. See, the
Yes.
typical
So
torque
how
characteristic
can
of the
my question
electrical.
is, sir?
Typical torque characteristic of the motor is like this. Okay.
Yes. So, yes, sir. So my question is that how can we ensure that constant power mode is that means battery how can deliver constant power and constant torque mode?
See, it is not always constant power. Obviously, as I say, if the battery get discharged, the capacity as the battery discharges, the voltage will also come down. Okay, something.
Yes.
I mean, this is not an exact realistic way. That is why when the battery goes to lower SOC, your vehicle performance will also slightly reduce.
Okay.
You can't expect your vehicle to give you 0 to 100 kilometers in 10 seconds. Okay, obviously there will be some limitations at every battery pack's bottom out. So you need to have some buffer, okay, to tell that okay, this is just fine to still have a performance. So obviously the performance of the motor reduces with respect to the given input from the battery. At how it behaves at 100% SOC is different. How it behaves at 10% SOC is also different.
Okay. No, sir. I'm asking that some starting portion, na, sir. That is a constant torque portion.
Mm-hmm.
Okay, but
Right.
the torque is also variable with respect to speed and roads and everything.
Mm-hmm.
Now the portion is started a constant power portion and the torque is reduced. Okay. So SOC and the voltage both are reduced when the discharge the battery. Then how can we achieve the constant power mode? That is my questions.
See, either the battery voltage when it comes down, you need to compensate that possibly with an additional current. Okay. The thing is, when the battery, let me just try to draw it. I think it's challenging to explain over how I can write it here. So when the battery is here, right? Imagine this is
okay.
Here you're able to get, let's say 50. I'll just write it here. 56 volts. Okay.
Yes.
And then maybe at this point here, you're only getting 48 volts. Okay. And
Okay.
then at some point here, you're getting, let's say 42 volts. So the voltage is reduced, right?
Yes, sir.
So, but what you're asking is, I want, let's say, 1000 watt here, example. So what I have to do, I have to draw an X amount of current from here, right? 56 volts multiplied by, what is the current I have to draw? Basically, power is equal to V into I, right? So if you put the math back, you have to draw, if I have to show you.
1000 by 56.
I'm sorry?
1000 by 56 ampere.
Absolutely, right? So 1000 by 56 will be, sorry, 1000, how much it will become? 1000 divided by 56. So you draw about 17.85 amp.
Yes.
Okay. Now what will be here? If you want 1000 watts, right? You have
Yes.
to draw obviously more current. That is, sorry, 1000. Right? 20.833. So this is how the variation. Okay, so you can achieve the output of the battery by compensating. Voltage will drop down, but you need to draw more current. Again, this will come to a limitation that at a certain SOC, the battery will not be able to give you the output as desirable you want. So there will be limitations on the vehicle performance as well later.
Okay, sir.
I hope-
Understand.
Yeah, thank you.
Thank you, sir.
Thank you. Thank you. Great, awesome. So I think we are coming to. I would really wish to continue this meeting, but due to some limitations of the time as well, we may have to slightly wind up the session on time. So what I wanted to kind of show across to our team is that the powertrain itself is a very big domain. So there is a lot of learning that you would like to have. Means we have fantastic courses at Decibels Lab. Anyway, those courses right now also available in our LMS, also in our offline sessions as well. If somebody is interested to explore about EV courses at Decibels Lab, please go down. We have a section of EV, okay, electric vehicle courses here. So we teach completely from basics, fundamentals to completely advancements to the all simulations and stuff like that. It will be a good learning opportunity for anyone if you're interested to explore about the programs on EV in place. So I'm sending this link. If somebody is interested, yes. So all the courses are listed here, which we showed here. Like we have master courses in powertrain development. It is a 9 months dedicated course. We also have a battery management system course. Then we have short-term micro specialization courses as well, like a 3 months long courses. And then there are small basic courses that are also available. To a basic to a advanced level courses are also available. So if anybody is interested, you can always drop in your interest with a Google form that we will sending it across to you, so that you can let us know how does it excites you to learn. So we will help you in all the teaching. We will teach you in all the parts of modeling the whole powertrain.
Sir,
Yeah, please.
hello, sir.
Hi.
Sir, for this, any fee payment or?
Yeah, absolutely. There's a fees. We have mentioned that fees in the website itself. Okay, nothing is hidden. If you go to each courses, there is a specific fee structure is there. I request you to visit this link, and then there's a fee structure for all these courses. You can definitely explore. Okay.
Sir, is there any internships?
Currently, we do not have internships. We have educational internships as well, where you can pay a nominal fee and learn on things like that. You can certainly explore.
Sir, there are no free internships.
Currently, we do not have.
And what about the placement options, sir?
So see, we have master courses where you have a 100% placement guarantee or a fee refund. That means you can join with a guarantee that we will help you in the placements, and obviously we will help you with the placements as well in the same way. These are 9 months programs where we will teach you from very, very fundamentals to the complete advanced syllabus, so that you can be as competitive compared to a 1 or 2 years experienced engineer in the industry. We have all the testing facilities. Right now, our offline center is in Bangalore. It's one of the technically advanced centers. We have a chassis dynamometer, we have a thermal testing chamber, we have a cell testing equipment and things like that. A vehicle testing lab, so that you can come in there. It is almost like a small foreign university lab that is available. We are based in RV College, so you can definitely undergo all the practical activities at our center. We also have a blended learning. You can learn online. Also, part of the courses you can learn offline as well. So, or we also have started recently offline courses as well. You can come to office every day and learn through the courses as well. That programs are also available. Great. Any other questions from anyone? And Vinayak, if you have any instructions for the certification, so please go over to it.
Sir,